Good morning, everyone. Welcome to my YouTube channel. So, for today's discussion or video presentation, I will be discussing a continuation of the rectangular footing design. No? So, another sample problems tayo. Then, after sample problems, one sample problems, continuation tayo, which is design of square and rectangular spread footing pa rin tayo. Pero yung loads is incorporated na natin yung earthquake. No? So let's continue solving problems. So we have here problem number one, number two for the rectangular footing. Design a rectangular footing having a base ratio of B is equivalent to 0.6 of L in meter. The bottom of the footing is located 2.5 meter below the finished floor line. The soil properties are shown in the figure. Assume F prime C is equivalent to 20.7 MPa and Fy is 415 MPa. Allowable soil bearing capacity is equivalent to 240 kPa. Unit weight of the concrete is equivalent to 23.5 kilonewton per meter cube. And design the dimension of the footing and determine the required steel reinforcement using 25 diameter bars. Also, we assume that the concrete cover, which is not stated in the problem, is equivalent to 75 And as you can see in the figure, we have here the loads. We have here live load, which is 900 kilonewton, and the dead load, which is 1,200 kilonewton. We have also concrete thickness for flooring, which is 150 and we have also on-fill soil, which is 200 thickness with the unit weight, which is equivalent to 17.5 kilonewton per meter cube. We have also a unit weight for the excavated soil, which is equivalent to 18.5 kilonewton per meter cube. And as you can see, from the finished floor line up to the bottom of the footing, we have here 2.5 meters, which is stated also in the problem. No? Okay, so solve tayo. So same process pa rin tayo, no? So kapag tayo nagde-design ng footing, first is kukunin natin yung assumed thickness kung hindi siya given dyan sa problem. We need to get the assumed thickness of the footing by, yun nga, yung QA is equivalent kay force over area. Then after natin makuha yung thickness, uh, kukunin natin yung effective, no? Para makakuha tayo ng actual dimension ng footing natin. Then after natin makuha yung actual dimension, we will be getting the ultimate soil bearing capacity, which is the QU. After makakuha si QU, solve natin si effective depth by shearing or one-way shear or two-way shear or the punching shear. After natin makuha natin yung D, we will be choosing the effective depth, which is pasok doon sa dalawa, no, na kayang mag-resist ng shearing at saka punching. Then after natin makuha yung actual thickness, we get the steel requirements by yun nga, MU is equivalent kay VRUBD squared. Then after natin makuha yung steel requirements, since rectangle po siya, we have here two steel requirements, no? Along long and along short. Then after natin makuha yon, solve for area steel, no? So, makukuha natin yung RU dun sa MU is equivalent to VRUBD squared. Then, makukuha natin si Rho. Then, compare for Rho minimum and Rho max. Then, after natin ma-identify kung ano yung Rho yung gagamitin, we could get the steel requirements, which is AS equivalent kay Rho BD. After makuha si AS, divide by area of bar para makuha natin yung number of bars, no, na needed dun sa ating design ng footing. Also, kapag nakuha na natin yung number of bars, we could get the spacing, no, na required para dun sa ating design. Okay? So, para mas maintindihan natin, ipakita natin kung paano siya sinusolve. Okay. So, we have this figure based dun sa ating problem. So, to solve, we have here the dead load, which is 1,200, and the live load, which is 900 kilonewton. So, yun yung applied load natin. So, solution tayo. We have here QA is equivalent kay force all over area. So, we all know that QA is equivalent kay 240 kPa based on sa ating problem. Is equivalent kay applied load, which is 1,200 plus 900 kilonewton divided by B is equivalent kay 0.6 of L daw. So, we have here 0.6 of L times the L to get the value of area, no? So we have here L is equivalent kay, lagay natin yan dyan sa problem. So we have here square root of 1,200 plus 900 divided by 0.6 multiplied by 240. So, dinaretso ko na siya sa calculator ha. Transpose nyo na lang. So, we have here the value of L which is equivalent kay 3.8188 meters. Then, therefore, the value of B is equivalent kay 0.6 ng 3.8188. So, we have here 2.2913 meter. Okay? So, since meron na tayong L, or the longest dimension, we could get the assumed thickness. So, we have here HC is equivalent kay 20% of the longest dimension, which is 3,818.8. Make sure that the unit is uniform. So, plus 75 mm. So we have here HC is equivalent kay 0.20 multiplied by 3818.8 plus 75. So we have here 838.76 mm. Okay, after getting the assumed thickness of footing, we could get the effective soil pressure QE is equivalent kay QA, allowable soil bearing capacity, minus itong pressure dito, no, ng concrete, which is unit weight ng concrete, H concrete, minus unit weight ng second layer ng soil, H ng soil, minus itong pang tatlong layer, which is unit weight soil, H soil, then yung concrete thickness natin ng footing, unit weight concrete, H concrete. Therefore, effective soil pressure is equivalent kay 240, which is given, minus unit weight of concrete, which is 23.5, multiplied by height of concrete. The height of first concrete natin is the thickness of the flooring, which is equivalent kay 0.15 or 150 mm. Minus 17.5, the unit weight of the first layer or unfill soil, multiplied by the thickness, which is 0.2 or 200 mm. Minus the third layer, which is equivalent to 18.5, multiplied by the thickness. Ang thickness ng ating third layer is equivalent kay 2.5 minus nito minus nito. So we have here 2.5 minus 0.35 minus 0.83876 minus 23.5 multiplied by nung height nitong nandito. Okay? So we have here 0.838.76. 0.83876. Okay? So we have here QE is equivalent kay, lagyan natin sa calculator. We have here 240 minus 23.5 multiplied by the thickness, which is 0.15, minus 17.5 multiplied by 0.2. Then we have here minus 18.5 multiplied by 2.5 minus 0.35, which is the height niyan, minus 0.83876 minus 23.5 multiplied by 0.83876. So we have answer, which is equivalent kay 189.0062 kPa. Okay. After natin makuha yung effective soil pressure natin, we could get the actual dimension of the footing by QE is equivalent kay force over area. We all know that QE is equivalent to 189.0062. Then the force applied, which is 1,200 dead load plus 900 live load all over 0.6 L times L. So we have here the value of L is equivalent kay square root ulit, square root of 1,200 plus 900 divided by 0.6 times 189.0062. So we have here 4.3032 meters. Then for the value of B, which is equivalent kay 0.6 ng 4.3032. So we have here 2.5819 meters. Okay? So this will be the actual dimension of our footing. Then after natin makuha yung actual dimension, which is the length and the width, so we could get the value of ultimate soil pressure, CQU. So we have here QU is equivalent kay factored P all over area. Okay? So we have here formula. Factored P is 1.2 ng dead load, 1,200 plus 1.6 ng live load, which is 900 divided by dimension, which is 4.3032 and 2.5819. Okay? So I hope na makikita po nyo pa yan. So QU is equivalent kay, we have here 1.2 times 1,200 plus 1.6 ng 900 divided by 4.3032 times 2.5819. Okay, so we have here 259.2158 kPa as the ultimate soil pressure QU. Okay? Titin ko lang to. L is equivalent kay 4.3032 meters. Okay? Yan. Ay, 900. Okay, so since may QU na tayo, so pwede na tayo mag-compute ng effective depth, no, by shearing and punching shear. But we all know that since rectangle siya, meron tayong shearing along long and meron tayong shearing along short side, no. Okay, so tayo. We have here one-way shear. Same formula lang din ng along long and along short, no? So we should say na along muna tayo, cut at long side. So puputol tayo sa may long side. Okay, so kung ito yung natin, so kung ito yung pundasyon natin, tapos meron tayong QU dito, ito si QU, then meron akong column, then yung critical section is distance D from the face of the column, tama? So ito yon. So pag kinat natin yan, ito, di ba makikita nyo ito? Tapos meron akong effective soil pressure din dito. Okay? So we have here this is equivalent kay B. Tapos yung distance na to is equivalent kay L minus column dimension all over 2 minus D. Okay? So, para makuha natin, we have here VU is equivalent kay VBC. And we all know that VU is equivalent kay QU area shaded, no? So, we have here QU, tapos yung area shaded ay itong part na to. No? Okay? We have QU which is equivalent kay 2, sulat ko muna, QU area shaded is equivalent kay phi times 0.17 lambda the square root of F prime C BWD. Okay? So we have here QU which is equivalent kay 259.2158. Area shaded is, sabi ko nga ito, tapos yung BW. So we have here L which is equivalent kay 4,330 at 303.2 minus the dimension of column which is 400 all over 2 minus D. Okay? Then yung BW dito is equivalent yan sa ito, yung plane na kung saan ay napunit, no? So lalabas yung B dito, yung BW dito at yung B dito, kasi meron pang BW dito para makuha natin yung area shaded. So pwede ko nang hindi siya isulat, no? Para hindi siya access sa space. Okay? So we have here, maka-cancel out naman kasi siya, no? Kaya pwede natin hindi siya isulat. We have here phi which is equivalent kay 0.75 multiplied by 0.17 lambda which is 1 square root of 20.7 the Fy. Tapos yung BW hindi ko na isusulat, cancel out. Then yung D is 1,000 D. Okay? So yung 1,000 dyan is the conversion factor para ma-convert natin itong PPA na to into MPA. So we have here D is equivalent kay 259.2158 multiplied by 4303.2 minus 400 divided by 2 minus alpha x, then equals 0.75 multiplied by 0.17 the square root of 20.7 multiplied by 1,000 D. Then shift solve. So we have here the value of D which is equivalent kay 602.7429 meters, mm. Okay? So we have here, ito is along, cut sa long side, no? So, pag nag-cut tayo sa short side, cut short side, so we have your formula ulit, VU is equivalent kay BC. So, QU, area shaded tayo, is equivalent kay phi multiplied by 0.17 lambda the square root of F prime C BWD tayo. Okay, so kung ito yung footing natin, tapos meron akong QU dito, then meron akong column, ito. Tama bang kapag nag-cut ako sa short side, ito yung short side natin B. So, pag nag-cut ako, distance D from the face of the column, so meron akong distance D dito. Tapos, kakat ko, yan. Okay? Sana naiintindihan niyo pa yan. Okay. So, i-isolate ko yung, yung ito. Tatanggalin ko. So, magiging ganito yung itsura niyan. Okay? So, ganyan. Then, meron akong QU dito sa ilalim na pasunod din sa area ng natin. So, lalabas, itong distance na to is equivalent kay B minus column dimension all over 2 minus D. Okay? So, babaliktarin lang natin siya. Okay? So, we have here 259.2158 multiplied by, so kung ito ay 4,300, yung B naman ang ilalagay natin dyan. Okay? Then we have here the L. So, yung B natin ay, the dimension ay 2581.9 minus 400 divided by 2 minus D times yung L. Pero yung L, maka-cancel out pa rin naman yan mamaya, no? So, we have here equivalent kay BC, PBC, which is 0.75 times 0.17 times 1, which is the lambda, the square root ng 20.7 times yung L. Yung BW kasi is yung area na kung saan is yung may punit, no? Ito yon. So, kapag itong part na to. So, meron akong L dito, maka-cancel out lang din naman siya later, no? Then, multiply by 1,000 D. Okay? So, again, 1,000 is the conversion factor. So, we have here D is equivalent kay, okay, so we have here 259.2158 multiplied by 2581.9 minus 400 divided by 2 minus D equals, tatagal ko na yung L, 0.75 multiplied by 0.17, the square root of 20.7, then 1,000 D. Ship sold. So we have here 336.9349 935 9350 mm. Okay? So yun po. Okay, so check for punching shear naman tayo. So we have here punching shear. So we have VU is equivalent kay VC. So VU is Q area shaded pa rin tayo. Is equivalent kay phi times 0.33 lambda the square root ng F prime C BOT. Okay? So kapag punching naman tayo, ang consideration natin na ito. Itong part na nandito. Itong napunit na to. Okay? So yun yung kailangan nating kumpitin. Okay? So yung area shaded natin dyan is itong part na nandito. Okay? Then yung BOD dyan is yung area na nandito. Kumbaga, kung itong sa loob na to, itong mga nanditong part, yung skin niya. Okay? So, para makuha natin yan, so we all know that ito L, ito si B. Then, we all know that this one, para makuha natin to, perimeter lang yan, 4 times 400 plus D. Kasi nga, from the face of the column is 0.5 sa kabila, 0.5 din sa kabila. So, we have here 1D, no? So, magiging 400D yan. Okay? So, solve natin. We have here QU, which is equivalent kay 259.2158 multiplied by area shaded. The area shaded is equivalent kay the dimension of the footing, yung buo, 4303.2 multiplied by 2581.9 minus yung area ng na-punch, which is equivalent kay 400 plus D squared. Okay? Equals phi, which is equivalent kay 0.75 multiplied by 0.33 times 1 times the square root of f prime c, which is 20.7 multiplied by 4 times 400 plus d, which is the perimeter ng ano natin, punch area, times the thickness, which is 1000 d. Again, the 1000 here is the conversion factor. Okay? So we have here d is equivalent kay 259.2158 multiplied by 4303.2 times 2581.9 minus 400 plus d squared equals 0.75 multiplied by 0.33 square root of 20.7 multiplied by 4 times 400 plus d times 100d ay 1000d. So we have the value of d, which is equivalent kay 589.3475 3474 mm. Okay. So hanapin natin yung value ni D na kung saan is pasok sa lahat ng ng shearing. Sa punching shear at sa one long side and short side. So we could say that this value is papasok dun sa lahat, no? Kasi kapag ginamit natin to, hindi siya pasok dito, hindi din siya pasok dito. Kapag dito naman, hindi siya papasok doon, no? So yung pinakamalaking value ng D ang kukunin natin, okay? So we have here this value of D na gagamitin natin as thickness ng ating pundasyon. Okay? So yan. So after natin makuha yung D, kukunin natin yung actual thickness T. Tama? Okay, so we have here thickness of footing is equivalent kay D, which is equivalent kay 602.7429 plus concrete cover, which is 75 mm, plus we all know that the concrete cover is ito. Ito yung pundasyon natin. We all know that the concrete cover is distance from the face of the concrete up to the nearest face ng steel bar natin. So ito yung 75 mm na yan. Okay? And we all know that the effective depth is from the center no main ng bar up to doon sa top ng compression side natin, which is equivalent kay effective depth. Ayan. So we have here this 1.5 diameter of bar pa. So we could add here na doon sa ating equation. So meron tayong plus 1.5 diameter of bar, which is equivalent kay 20. Tama ba? 20 mm ang ating diameter ng bar. 25. Pala. 25. So we have here thickness is equivalent kay, dito ko na lang isusulat para hindi aksaya sa space. We have 602.7429 plus 75 plus 1.5 multiplied by 25. So we have here equivalent kay 715.2429 mm. So this will be the dimension of our the thickness of our footing. Okay? So after nating ma-check yung area at saka yung dimension, yung actual dimension ng footing and the thickness, so we could proceed to the next step, which is the steel requirements, no? So we have here steel requirements. Okay, kapag pinag-usapan natin si steel requirements when it comes to rectangular footing din, mayroon tayong dalawang side pa rin, no? Kasi nga magkaiba yung MU ng bawat face, no? Yung sa along long and along short side na requirements natin. So first, let's solve for the steel requirements for along long or kasunod dun sa long. Kung along long tayo, kung ito yung ano natin, we have here L and B. Pag along long, yung steel requirements na kinukumpute natin ay itong pag ganito. Okay? So, along long. So, we have here, so kung ganyan yung bar natin, ang cut natin ay pag ganito. Okay? So, sabi tayo. MU is equivalent kay phi RU BD squared. Okay? So, para makompute natin yung MU, pakita ko sa inyo kung ano yung MU na yan. So, kung meron tayong column dito, at meron tayong pundasyon na to, ito ay si D. Then we have here unit width of ultimate soil bearing capacity QU. Ito. Then, kapag kukunin natin yung MU, ito ay si L ha, ang length nito ay L. So, kapag kukunin natin yung moment MU, tama bang ikakat ko dito sa critical section which is the face of the column. So, kapag kukunin ko yung MU, tama bang itong uniformly distributed na yan, so sabihin ko ito yung distance ay X, which is X is equivalent kay L minus 400 or the column dimension all over 2. Okay? So, lagay ko muna siya as X. So, we have here formula for MU. MU is equivalent kay QU multiplied by the distance X, tama, times X over 2 para dun sa magiging resulta niya, perpendicular distance, multiplied by B, which is yung nanditong part ng B. Okay? So, same din dun sa, kapag dun sa along short, ganito din yung mangyayari. So, we could say that the formula is QU X squared all over 2B. Okay? And we all know that X squared, yung X is equivalent kay dito. Okay? So, write natin. We have here QU which is equivalent kay 259.2158 multiplied by X natin. We all know that X is equivalent kay L minus CD over 2. So we have here the actual length which is yung L ganyan dito. So we have here 4,000 ano ba dimension natin? 4,303.2 minus the column dimension which is equivalent kay 400 divided by 2. Yan yung value ng X. Then dito, naka-squared siya. So squared all over 2. Okay? Equals. Yung B dito at yung B dito ay pareho lang naman yan. So pwede kong i-cancel out. Pero para for the sake na ma-identify nyo, so lagay ko na lang siya. So we have here B which is equivalent kay 8.9 equals, erase ko na to equals phi which is 0.9 for bending, then RU which is unknown, yung hinahanap natin, B is equivalent kay 2581.9 times D which is equivalent kay effective depth natin is 602.7429 squared times yung conversion factor natin which is 1,000 dito, no? So, pwede kong isulat dito yung 1,000 pero pwede din dito. So, 1,000. Okay? So, we have here RU is equivalent kay, lagay sa calculator, we have 259.2158 multiplied by 430, wait lang, 430.3.2 minus 400 all over 2 tapos squared all over 2. Hindi ko na isusulat yung 2581.9, no? Alpha equals 0.9 alpha x times 602.7429 squared times 1000 b. 1000 lang pala. Times 1000 as conversion factor. So we have here 1.5. So we have here RU is equivalent to 1.505 098 MPa. Okay? So that's the value of RU. Then after getting the value of RU, so we have here rho is equivalent to 0.85 F prime C all over Fy multiplied by 1 minus the square root ni 1 minus 2 RU over 0.85 F prime C. Okay? So we have here 0.85 F prime C, which is equivalent kay 20.7 all over 415 multiplied by 1 minus the square root ni 1 minus 2 RU. The value of RU is equivalent kay 1.5098 all over 0.85 F prime C, which is 20.7. Okay? Equals. So we have here the value of 0.003809. Okay? Then check for rho minimum. So dito tayo rho min is equivalent kay 1.4 all over Fy. So the value is 1.4 divided by Fy, which is 415. So we have 0.003373. Okay, so use this one kasi si rho is mas malaki pa kay rho min, no? Pero double check mo pa siya kay rho max, no? Pero alam ko mas point something lang yung rho max, 0.0 something lang. So pwede na natin hindi i-consider, no? Okay, pero yun nga, for the sake na ano, is i-compute nyo din si rho max para maano natin yung ano natin dito. Okay, so we have here this rho. Para makuha natin si AS is equivalent kay rho BD. Okay? So si rho is equivalent kay 0.003809. B, yung B natin is yung actual B, which is 2,581.9 times yung D, which is 602.7429. So we have here AS is equivalent kay 0.003809 multiplied by 2581.9 times 602.7429. So we have here the AS is equivalent kay 5,927.6492 mm squared. Okay. Then, after natin makuha si AS, we have your number of bars, which is equivalent kay AS over area bar. So, we have here AS, which is 7.6492 all over pi times 25 squared all over 4. So we have here 592.646492 divided by pi times 25 squared all over 4. So we have here 12.076 pieces. So we could round up siya as 13. Kasi 12.1 ng ano niyan eh, no? So kapag ano natin, round up as 13 pieces siya. Okay? Pag 12.04 yan, round down tayo, no? Okay? So we have here spacing. Spacing is equivalent kay B, which is 2581.9 minus 150 all over 13 minus 1. So the spacing is equivalent kay 2581.9 minus 150 divided by 12 equals. So we have here 202.6583 or say 200 mm spacing. Okay? Okay. So, along-long pa lang yung nakakompute natin na reinforcement. So, let's compute for the short side of reinforcement. Still, requirements. Along short tayo. Okay? So, kung along short, so dapat yung bakal natin is pasunod dun sa short side. So, kung we have here L and B, so yung bakal natin is pag ganito. Okay? Yan yung along short side. Pero, yung cut natin dyan is pag ganito. Okay? Yan yung consideration natin. So, kapag ano tayo, may column ako dito. Tapos, meron akong footing. So, dito ang part na to, yung ikakat natin. Okay? So, pag i-isolate ko yan, so we have here this one. Tapos, meron akong QU dito sa ilalim. Okay? Okay. So, and we all know that this distance is equivalent kay B minus column dimension all over 2. No? Kasi from the face of the footing tayo, face of the column. Okay? So, we have here MU is equivalent kay P RUBD squared. Okay. Then, same formula pa rin tayo. Yung MU natin is equivalent kay QU times X squared all over 2 times L naman tayo. No? L naman siya. Kasi yung B natin ay dun sa X squared. Okay? So, we have here 259.2158 multiplied by X, which is equivalent kay the dimension of the footing, 2581.9 minus 400 column dimension all over 2, which is the value of X, so squared, divided by 2 multiplied by L. The value of L is equivalent kay 4,303.2 is equivalent kay phi RU B, which is equivalent kay 4303.2, then D, which is equivalent kay 602.7429 squared multiplied by the conversion factor, which is 1,000. Okay? So we have here D is RU is equivalent kay, solve natin. We have 259.2158 multiplied by 2581.9 minus 400 divided by 2 quantity squared divided by 2. Then, hindi ko na isusulat ulit yung 4,000. So, we have here 0.9 multiplied by alpha x times 602.7429 quantity squared times the conversion factor, which is 1,000. Okay? So, we have here RU is equivalent kay 0.4718 MPa. Okay? Then, again, compute for the rho. Rho is equivalent kay 0.85 F prime C B Fy times 1 minus the square root ni 1 minus 2 Ru over 0.85 F prime C. Okay. So we have here 0.85 multiplied by F prime C, which is 20.7, all over Fy, which is 415, multiplied by 1 minus the square root of 1 minus 2 Ru. 2 value of Ru is 0.4718 pala. 4718 all over 0.85 times 20.7 Fy. F prime C pala. So we have here 0.00 0.85 pala ta. Wait lang. 0.85. So we have here 0.001153. Then check for rho minimum. Si rho minimum natin is computed na siya kanina as equivalent kay 0.003373. Okay, so gagamitin natin is yung rho minimum. Kasi nga mas maliit ito. Ay sobrang liit nito kumpara dito, no? So we have here AS is equivalent kay rho min D. So we have here 0.003373 times B. Yung B natin ay yung magiging L, which is equivalent kay 4,303.2 times yung D, which is 602.7429. So we could get the value of AS is equivalent kay 0.003373 multiplied by 4303.2 multiplied by 602.7429. So we have here 8,748.6285 mm squared. Okay? Then after natin makuha yung AS, so we have here number of bars is equivalent kay AS all over A area bar. So we have here 8748.6285 all over area bar, which is pi times 25 squared all over 4. Okay? So we have here this one 6785 divided by pi times 25 squared all over 4. So we have here 17.82. So we can say that this is 18 pieces. Then for the spacing, is equivalent kay 2, 4,303.2 minus 150 all over 18 minus 1. So the spacing will be 4,303.2 minus 150 divided by 17. So we have here equals to 244.305 9. So let's say 240 mm. Okay? So this will be the design para dun sa ating pundasyon na kino-compute. Okay? Okay. So medyo mahaba siya, no? So wait lang. Ito, dito, tapos ito. Tapos yung is pa kanina, no, na in-erase ko. So sobrang haba ng solusyon niya. So may tanong kayo? Okay. Siguro tanong niyo, sir, ginagamit po ba yan sa actual, no? So usually kapag yung concept lang ang ginagamit natin dito, no? Kasi kapag sa actual, usually we use spreadsheets na kung saan ay direct na dun sa Excel natin may mga kumbaga formulated na yung spreadsheet natin sa Excel, then type mo na lang yan. Usually mga taga DP or mga uh, senior structural engineer may mga spreadsheets nilang ginagamit, no, para mag-compute. And also, syempre, through technology, may mga software na kagaya ng STAAD na ginagamit para sa pagde-design, no? May mga STAAD Pro, for foundation and for RCDC, no? Pero syempre, kayo bilang estudyante na nag-aaral pa lang, kailangan nyo malaman yung basic computations kung paano kinukompute talaga siya, no? So ganito po siya. So sobrang haba niya. So ginawan talaga siya ng paraan ng mga engineers para at least kung pag nagde-design ng bahay is madali na lang para sa atin yung convenience ng pagde-design, no? Okay. So ano pa ba mga possible questions ninyo na pwede nating sagutin, no? So if you have questions in mind, no, comment lang kayo sa chat box, then i-replyan ko kayo, no? Usually kasi mas maganda kasi pag mga face-to-face class to, no? Kasi nga sobrang haba ng computations na to, may mga estudyante talaga na naliligaw ng landas, no? Kumbaga sa kalagitnaan pa lang ay lutang na dun sa mga computations na kino-compute natin. Pero yun nga, good job na kayo ay nakarating sa 5th year at 4th year, no? So it's a great job yan na sa engineering ay nakarating na kayo dyan. Konting kembot na lang or konting push pa sa sarili para graduate at maging isang lisensyadong civil engineer. Okay? So, we have two problems for square footing and we have also two problems for rectangular footing. Para po dun sa mga estudyante ko na nanonood ng aking video, meron po akong pa-exam, no? Pero announce naman siya, i-announce ko siya sa ating group chat. Pero yun nga, klase to, no? So, dapat napapanood niyo yung aking video para at least it's part of your lecture and learnings na din, no? Okay. So, next topic natin will be design of a spread footing with an application of earthquake load design, no? So, ito is importanteng natin kasi nga we should incorporate earthquake load in our design kasi pag nagkaroon ng earthquake at yung building mo ay hindi naka-design for earthquake resistance, kung yung hindi makaka-resist ng earthquake ay possible masira agad siya or magkaroon ng mga cracks and lead to fatal, no? So we should consider earthquake resistance. So as you can see in this figure, di ba, we have portal method and cantilever method to solve the internal loadings na nangyayari dyan sa mga members na yan, di ba? Pero hindi na natin gagawin yon, no? Kumbaga, we assume na lang na value na applied nandito sa ilalim, sa pundasyon, no? So, hindi ko na kayo pahihirapan pa na mag-compute pa na ganito kasi usually naman may earthquake subject pa naman kayo. So, doon na lang kayo mag-compute. Pero syempre, Alam niyo naman kung paano yun kino-compute, di ba? So, cut, then V2, V2, V and V dito sa ilalim. Tapos, cut, isolate para makuha natin yung internal loadings, no? Theory 1 yan. So, yun. And I do hope na maintindihan niyo to kasi medyo mas mahaba to kumpara dun sa rectangular footing natin. Okay? So, i-discuss ko na siya para sa next video ko is computation na lang tayo, no? So, yun. Sabi ko nga kanina, we should incorporate the design, in our design, the earthquake load, no? Pero yung first computations natin with regards dun sa square and rectangular, hindi natin siya in-incorporate kasi nga, design siya ng actually loaded columns lang. Actually loaded means dead load, live load lang na vertical or perpendicular dun sa ating applied. Ito kasi, sa earthquake load is usually yung lateral force natin na kung saan is horizontal yung reaction niya or yung moment niya, no? Kasi as you can see dito, kapag nagkaroon ng earthquake, magkakaroon ng movement yung building natin which is pag ganito, no? Na kung saan yung movement na yon is magko-cause ng stress dun sa ating pundasyon, which is kung ito yung ano natin yung building tapos pinagalaw natin tong dalawa, tama bang nasa stress tong nanditong part sa connection? So, ibig sabihin kailangan nating i-consider yon, i-reinforce yon ng mabuti kasi nga possible dun magkaroon ng sira sa ating pundasyon. Okay? So, bago tayo mag-proceed, may papanood akong video no, na kung saan ay with regards dun sa earthquake at anong kahalagahan nito sa ating pagde-design. Okay?
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid sized buildings. Like a well timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
Okay, so as you can see dun sa video, thank you pala dun sa copyright. For the copyright purpose nung nilagay ko na yung pangalan dyan nung gumawa ng video, no? So, yun. As you can see dun sa ating video na kung saan ay yung kahalagahan ng earthquake na kung saan ay yung earthquake is caused dun sa ground shaking natin, no, in motion. Na kung saan kapag nag-shake yung motion ng lupa, is kasama din yung structure natin na kung saan is nakatayo dun sa ating dun sa lupa, no? So sabi dun sa sa earth, sa video na kung saan if your building will match the frequency of the yung paggalaw ng lupa, so ibig sabihin mag-withstand yung natin, yung structure natin, no? So, sabi nga dun din sa video, hindi porke mataas yung building mo or porke mababa yung building mo, tatayo yan kapag nagkaroon ng earthquake. It depends pa rin, no? Na kung saan ay, if you can match the frequency of yung soil type nga kapag nagkaroon ng movement, ibig sabihin, makaka-withstand yung mo, no? So, in the end, sabi dun sa video, it's not the size that matters, it's the performance or the quality, no, na kung saan ay mahaba yan or maliit, basta yung performance yung diyan, yung babasihan pa rin or yung quality nung pag yung quality nung building mo when it comes dun sa pagyugyug nung earthquake or pag ganun ng earthquake sa'yo, no? So yan. Okay, so let's proceed to the design criteria for footing or yung steps in designing a footing with earthquake or with yung bending yung moment natin. So, first step is parang same pa rin naman siya. QA is equivalent kay force all over area. Yun nga lang may bending siya kaya may plus 6m over BL squared. Okay? Or yung 6m ay MC over I, no? Okay. So, para makuha natin ulit yung assumed thickness. Then, QE, para makuha natin yung effective soil pressure. Then, balik ulit tayo dun sa force all over area plus 6m over BS squared. Or, MC over I. Okay? So, makuha natin yan dyan yung dimension ng ating footing. After natin makuha ulit yung dimension ng footing, getting the QE tayo. So, kapag may moment tayo, ang QU po natin ay dalawa. We have QU minimum and QU maximum. Ibig sabihin, meron tayong trapezoidal soil capacity sa ilalim ng ating lupa, no? So kapag may trapezoid tayo, yan na yung pinakatakutan ng lahat, no? So kapag nagsosolve tayo ng trapezoid, ay nakakasawa na. Kumbaga sobrang haba kasi ng solusyon yan. Okay? Pero yun nga, kailangan nyo pa rin intindihin yan. Then we have also this one-way shear and two-way shear. Napapakita ko naman sa inyo kung paano siya kino-compute. No? Papakita ko lang muna sa inyo kung paano yung mga steps in designing. For the step 3, flexure pa rin tayo. Halos pareho lang naman siya ng steps. Ang pinagkaiba lang niya talaga is yung may MC over I tayo na kino-consider. Then syempre kapag kino-compute kasi yung VU dito sa one-way shear tsaka two-way shear, iba din po yung process niya. Pero syempre, ipapakita ko naman siya sa inyo, no? ng detalyado para at least mag-gets ninyo. Okay? So, we have these sample problems. So, kung gusto nyong unahan ako mag-solve, pwede nyo namang isolve yan, no? Or pwede natin gawing assignment sa aking mga estudyante, no? But, yung next video ko, i-present yung solution yan. Kasi parang aabutin niya ng mga 30 minutes or 45 minutes in solving that problem. Okay? So, this will be the end of my video. Siguro mga uh, mag within this week din, no? Or bago mag-Monday siguro mag-send din ako ulit ako ng video ng computations niyan. No? And I do hope that na naiintindihan niyo yung discussion ko dun sa additional problems with regards dun sa rectangular footing and as well as dun sa pag-discuss ng earthquake, no? And sana pare-pareho tayo mag-adjust sa ating klase na kung saan ay ang hirap talaga kapag online class, no? Kailangan natin na ah, may gadgets, no? Pero hindi ko naman kayo nire-record na magkaroon ng high-end gadgets, no? As much as possible nga, kaya ako ginawa tong video na to para at least hindi man live stream ng bata during discussion, at least naka-record siya. Kumbaga mapapanood pa rin ng estudyante, no? So, I do hope that this video will help you to gain more knowledge when it comes sa design ng pundasyon, no? Pero yun nga, concept lang naman to, no? Ang dinidiscuss ko, no? Pero sa actual world, hindi na rin naman siya nagagamit. Pero syempre, kailangan niyo siyang gawin. Or, para lang dun sa information or additional knowledge na pagdating sa site, ay alam niyo yung gagawin, no? Ganito yan. Pero yun nga, ito naman, yung mga ganitong problem ay bihira naman siya sa board exam. Usually, madali lang yung process sa board exam, no? Tuturuan naman kayo, or tuturuan ko kayo on the later part kung paano yung pag nagsisolve kapag sa board exam ng ganitong mga problems, no? Okay? So, ingat po tayo, keep safe kasi may COVID pa rin, no? So, ipanalangin natin na sana magkaroon ng lunas itong sakit na to at mawala na. So, ingat po tayo. So, yun. Goodbye. So, pag may mga questions po kayo, you can message me or you can comment dun sa ating YouTube channel, no? Then, re-replyan ko po kayo. Huwag po kayong mag-alala. Open-minded po ako, no? So, kung may error po man din dun sa aking video, you can also check it, no? Or pwede nyo i-correct. Okay? So, thank you sa panonood. Paki-subscribe na lang din at paki-notify yung sarili kapag para at least updated kayo na may uploaded video ako. Okay? Thank you.